Okay, so this is kind of continuing a little bit in probability. We're going to get into distributions here, which starts with the idea of random variables. So we're going to talk about discrete and continuous random variables. All right, so a random variable, usually we call them capital letters, oftentimes X, is like a container, okay? And it contains the possible values. So it contains possible values of a chance process. Okay, so if the chance process has a numerical output, okay, so like rolling a die or spinning a spinner or how many times does the baseball player get a hit during a baseball game or something like that. So some sort of chance process. The X is the values that could come out of that. So like a simple example would be like if you're just doing something like flipping two coins, right? If you flip two coins, you could have a 0, 1, 2 possibilities of getting heads, right? So like the sample space for that chance process is heads, 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 tails, tails, heads, tails, tails. These are the four possible outcomes. Each of them are equally likely. They all have a probability of 1/4, right? So what I've done here is I've taken my random variable and assigned it to the number of heads. So X is now the number of heads from flipping two coins. Okay, so that gives me a random variable. The second thing that we're going to get here is what's called a probability distribution. And what a probability distribution is a mapping of those values for the random variable to the probability of that value. So the probability of having 0 heads would be, well, just getting 2 tails, so it would be 1 in 4. The probability of getting 1 head is this or this, right? So it's or, so I would add the probabilities, which is 2/4 or 1/2. And then the probability of getting 2 heads is against 1/4. Now note, when you have a probability distribution like this, all of these values have to add to 1, right? So the probability distribution maps the value of the random variable to its probability, okay? So this is two big ideas here. Random variable is the container that holds the possible values for a chance process. The probability distribution, this whole chart, is an example of a probability distribution, is a mapping between the values and their probabilities. Now we get two flavors of this. We're going to get discrete and continuous. Okay, so discrete means that there's gaps. Okay, there's gaps between the numbers. So like 0, 1, 2, this is a discrete probability distribution because there's a gap between 0 and 1. And there's a gap between 1 and 2. Now, this one also happens to be finite. There's only 3 possible situations. But we could come up with a situation that's not too hard that would be both infinite and discrete. So let's see if we can come up with that. Okay, so let's say that, I don't know, like X represents the number of darts thrown before a player gets a bullseye. Right, so X would be the number of darts thrown, right? And then, well, like, you'd have to have 1 is the smallest number, right? 2, they could have 2 darts, they could have 3, they could have 4, they could have 5. But as you can see, this could keep going on and on and on and on, right? So they could, in theory, throw an infinite number of darts and never hit the bullseye, right? So the probability distribution here is set up this way, right? That you can do this. So the distribution would be then the probability of X, and we don't, like, we'd have to have some more information in order to establish, like, because this is just going to be the probability that 1 dart is thrown, this is the probability of 2 darts is thrown, this is the probability of 3 darts is thrown, and then all the way to the end here. And believe it or not, if you add these all up, probability of 1 plus the probability of 2 out to the probability of infinity, how do you do that? It's going to equal to 1. But this is still discrete, right? Because there's gaps between things. Like, you can't have 1.7 throws. Okay, so there's a distance between 0 or 1 and 2. This is still a discrete probability distribution. In fact, later on we're going to learn that this is what is referred to as a geometric distribution. So we will see about learning a little bit about the geometric distribution a little bit later on, but this is an example of a discrete probability distribution where the random variable can take an infinite number of different values, and you can get a finite probability for each of those values that, even though there's an infinite number of them, it will add to 1. Now note, I've called this geometric. Some of you might recognize that a geometric series, if it is infinite, has the possibility of giving a finite number. This comes from calculus, but that's not something you need to know specifically for this course, but these things are all related. Okay, so this gets us to the idea of a discrete probability distribution. They're ones that have gaps between the values that the random variable can take. Okay, so now we need to get into, like, what is a continuous probability distribution. Okay, so in a continuous probability distribution, we tend to look at an interval, right? So let's say, like, 0 to 20, right? And it may be something where the question is like, what is the probability? So let's say this is like 0 to 20 years, right? So, like, what's the probability that the light bulb will burn out over a particular period of time? So, like, in this situation, we know that, like, the brand new light bulb, like 0 years, is not likely to burn out, but the light bulb, like, at 20 years is more likely to burn out, right? So this probability is, like, increasing over this, right? And now, if I took this out to positive infinity, I would know that the probability, the total of the probability would have to be 1, right? So what we're going to do here is we're going to get what's called a probability distribution function, right? And what's going to happen here is we're going to, like, say, like, if I make this, let's say, 15 years and this 20 years, then the area of this part, the area of that, will equal the probability that my random variable x, well, I have to kind of be careful with that. My random variable x is going to be between 15 and 20 years, right? So this would be the probability that like I am needing that to happen. So if you're thinking about this, like there's some sort of continuity here because the light bulb could burn out at any given time. It could burn out at like 15 years, 15.265 years, right? It could burn out at that. So it is, there are no gaps between the values that x can take. Like x can take any number from 0 to infinity, right? So in this example, in fact, you've actually seen a probability distribution that goes from negative infinity to infinity. And it looks like this. It's this bell-shaped curve, right? So the normal distribution is a probability distribution that goes from negative infinity to infinity, right? Where like the random variable is distributed normally. So like if I had a normal distribution, right, let's say this has a mean of 0 with a standard deviation of 1, and I want the probability that my random variable is greater than or equal to 0, then I know that that is 0.5, right, because the area under the curve here is half the curve, right? We did some work with this with like the empirical rule and things like this with the normal distribution. So the normal distribution is an example of a continuous as opposed to a discrete probability function. Now, we're going to see a little bit deeper on this, that there's more than just the normal distribution here. There are other continuous distributions. Big ones that we work with in this course are what are called the normal distribution, another one called chi-squared, which is about figuring out goodness of fit and independence, and you get another one that's called a t-distribution, which is similar to the normal distribution, but the normal distribution, you need to know the standard deviation, and the t-distribution, you do not. You just need to know the sample size from which the distribution was sampled from, but we will get into this. So the big takeaway for today is this, that random variables are containers. They are containers that hold the possibilities of a chance process. If there are gaps in what values it is possible for that container to hold, those are discrete random variables, and we usually give their possibility distributions by using a table or maybe an equation or something like that. If the random variable can hold values that are like segments of the real numbers that don't have gaps in between them, then we call that a continuous probability distribution or a continuous random variable, and it gets a probability distribution using a density function, which is what we're looking at here. And the prime example that we've seen of that so far has been the normal curve. All right, so this is kind of like a 10,000 foot level of like distributions and probability distributions, just getting at the idea of random variables and how they're distributed. And we'll put some more detail to this as we move forward. So see you next class. Awesome. Thank you.